so much, Nick, for that introduction of everyone. I'm Katelyn, a third-year PhD student in the Human-Computer Interaction Institute at Carnegie Mellon University, where I focus on human-AI collaboration and transparency mechanisms to help improve that collaboration between the human and AI. And then we have also Philipp here.
Yeah, thank you. Thank you, Nick, for the introduction. So my name is Philipp. I am a third-year PhD student based in Germany. I am at the Karlsruhe Institute of Technology. Within my research, I'm mainly focusing on human AI collaboration. So basically how to make those systems more efficiently, but at the same time also focusing kind of at the knowledge aspect of how can we actually like capture humans' expert knowledge and then distribute it within organizations. So basically to use AI and XAI for training purposes.
Awesome. So based on that, we'll start our talk. Let me set everything up here. Okay. Let's make sure it moves forward. I didn't want to do that. Okay. Hi, everyone. So today, Philipp and I would like to present our team's ongoing work about imperfect explainable AI, which we'll refer to as Imperfect XAI, and the impact that it has on human AI decision-making. And this work, as I mentioned earlier, has been accepted to CSCW 2024, and we will present it there in November. So when we refer to high-stakes visual decision-making, we're referring to numerous computer vision-based applications that require decision makers to visually search or analyze images or video input. For example, radiologists can diagnose diseases from X-rays, humanitarian aides can assess building damage after wildfires or other catastrophic events from satellite imagery, and conservation workers, as we have on here, can also investigate the impact of conservation policies on wildlife through camera trap data, for example. But ultimately, the accuracy and accountability of these tools are vital. As such, decision makers need transparency mechanisms, such as explanations about how and why these tools make predictions. But what if the transparency mechanism provides wrong information for that how and why? So let's look at an example of how a transparency mechanism could provide wrong information to us. So in the domain of bird species classification, even though the AI correctly predicts here that this is a cerulean warbler, the generated explanation, which is actually from a model, we didn't fabricate this, does not completely align with the predicted class of cerulean warblers, and nor the image, because cerulean warblers do not have gray heads, and in the image we can see that it actually has a blue head. So this is a really interesting phenomenon that we dubbed imperfect XAI. Formally, we define imperfect XAI as the phenomena where an explanation reveals evidence that does not necessarily comply with the prediction. And we view this term to be an umbrella term to encompass other terms that have been introduced in the field, such as explanation fidelity or explanation faithfulness. We can also see this phenomenon of imperfect XAI in another type of transparency mechanism, example-based explanations. And in this case, the AI was correct in predicting the national warbler, but the generated example-based explanations are misleading and do not show any pictures of a national warbler. This is also an imperfect XAI technique. So finding multiple transparency mechanisms to be imperfect led us to conceptualize how imperfect XAI impacts human-AI collaborations. Previous conceptualizations of human-AI collaboration, such as this one from Schemmer et al., outlined 4 different avenues of decision-making that humans end up taking when collaborating with AI. For example, in human-AI collaboration, the human can initially be right about their classification, which is represented by the green check here, or they can be wrong, represented by the red X. And the AI advice can also be correct or incorrect about the classification. So when the human does not follow the AI advice, when they are wrong and the AI advice is correct, then this is known as under reliance. If the human follows the AI advice when the advice is incorrect, then this is over reliance. And if the human overrides the AI when the advice is wrong, then this is correct self-reliance. And lastly, when the human is initially wrong and they do not rely on the AI advice when the advice is correct, then this is And they do rely on the AI advice when it's correct, and this is correct AI reliance. So in our study, we introduced Imperfect XAI so we can expand upon that conceptualization to now include this extra column representing the correctness of explanations, which we simplified here to be a binary case of either always being completely incorrect or completely correct. So now we have two cases for each of those four scenarios that I just went over. For example, we have two for when under-reliance occurs, one for when the explanation is correct, and one for when it's incorrect. And similarly for over-reliance, this now occurs for correct and incorrect explanations. But alternatively, if the human were only to correctly rely on the AI when they were wrong and correctly override the AI when the AI is wrong every time, then they would reach complementary team performance, which is when the human and AI perform better than the AI or human alone. And now I'm going to switch it over to Philipp.
Yeah, thank you, Katelyn. So with our new conceptualization, we are basically now able to investigate the impact of incorrect explanations, or more or less imperfect explanations, on the decision maker. And we can also by that include like other factors of the decision maker, for example, his level of expertise. So let's assume we have an example bird, and this example bird in this case would be a white crowned sparrow. Okay, so let's see that we want to look into how a decision maker now decides in such a case. So let's assume there is an expert. Let me see whether the animations are working now. No.
Oops. Zoom. There we go.
Okay, perfect. Yeah. So let's assume that an expert already knows that this is a white crowned sparrow, despite that the explanation might be convincing and aligning with the image. So basically what the AI is saying here, this is a dark-eyed junco, which is the wrong prediction, but the explanation is incorrect as well, as it's actually not showing the, making the model more transparent and showing what the model actually predicted. But it's in this case aligning more or less with the ground truth images. So basically here the explanations are shown 3 examples of the actual image that is not aligning with the AI's prediction. So this is actually a case where it could be highly deceiving the decision maker. However, an expert has all this knowledge, so he may already be convinced, okay, this is not a dark-eyed junco. I know how a white-crowned sparrow looks like. However, someone with no expertise can be wrongly convinced by that. So basically relying on the wrong AI prediction and then coming up with something that is just wrong. So in this case, we would call over-relying, and in the end, such a non-expert could also learn, of course, something as the reasoning behind the AI's prediction is just wrong. So, okay, now it seems, did you just click or was that me? Okay, no. You can go one slide ahead, that's okay.
Oh.
Okay, so cool. Thank you. So formally, if we put that now into the framework that Kate just introduced, we can now formally actually calculate how the relative self-reliance is more or less impacted by such incorrect or correct XAI advice. So to sum up, let's first quickly introduce what it actually means when we're talking about relative self-reliance. So relative self-reliance are all the cases when a human is initially correct and then the AI is giving the wrong advice. So just in the case that we've seen. And then we are interested in all the cases. So basically when the XAI is correct or incorrect, how the human decides eventually. So basically whether the human is still coming up with the correct decision in the end. So basically relying on themselves. And this is what we call relative self-reliance. Now there also might be another case. So in this case, for example, we are shown this bird here, and the expert might already be familiar with that is a cerulean warbler. So the expert basically has the right knowledge, and also despite that the XAI explanation is incorrect, as the natural language text there is saying, okay, it has a white belly but a gray head, and obviously the bird has no gray head. The expert might not be deceived by this. However, a non-expert might not be familiar that the AI prediction is actually correct. So he just sees the explanation, but sees, okay, the explanation is incorrect because this bird doesn't have a gray head. But of course, the AI prediction is still correct. So in this case, the non-expert is actually not going with the correct AI prediction and is under relying on the AI prediction. So also in this case, of course, such a non-expert can learn the wrong things. And if we formalize that again, now in this framework that Katelyn just introduced, we can see the following. So here we're talking about relative AI reliance. So basically all the cases where the AI system was initially correct, but the human was wrong. So the human has this intention to come up to basically follow the AI advice. And by now bringing in this new dimension with the incorrect explanations, we can more or further investigate how the decision maker is actually impacted when the explanation is correct or incorrect, since this is actually in all studies that have been conducted so far totally neglected. Okay, so basically, based on all those scenarios, we came up with a research model. So first, we hypothesized that the correctness of explanations has an effect on the relative AI reliance. And also, of course, an effect on the relative self-reliance. So relative AI reliance and relative self-reliance are in the end the two factors that more or less form appropriate reliance, the term that we are focusing on when we are investigating those AI-assisted decision-making scenarios. But furthermore, we also think, or we also derive that the level of expertise, so basically the knowledge someone has, is moderating this effect of the imperfectness of explanations on appropriate reliance. And we also investigate how the assertiveness of such explanations is impacting this relationship of the correctness of explanations on appropriate AI reliance. And the assertiveness more or less focusing on the text explanations that are given in the XAI. So basically whether they are assertive, non-assertive, or whether they're neutral. And based on this research model, we came up with several interesting research questions. So first, we are interested in looking into, okay, how correctness of explanations is actually affecting appropriate reliance. So if someone can correctly rely on AI, and to what extent does actually those two factors that I just introduced, so the level of expertise and the assertiveness, moderate that effect? Well, then overall, we are also looking into how does complementary team performance impact the decision makers level, how does the decision makers domain expertise, so it's his or her level of expertise, impact the complementary team performance. So basically, how are in the end human and AI working together, and how does also the correctness of explanations impact this team performance? And as we might already suggest, incorrect explanations have the potential to eventually also deceive humans. That was the example that was given when we saw that the non-experts were deceived by those incorrect explanations, even though the AI was correct. So what we also interested in, so we also asked to what extent do incorrect and correct explanations deceive decision makers with different levels of expertise. While we could choose another decision making domain such as radiology or building damage assessment, in our study, we were actually focusing on people that are collaborating with an AI to identify bird species from images. So we are looking in our study in the bird imaging domain, and we chose this birding case because this task is similar to high-stake computer vision tasks. And we have a large pool of non-experts that are actually basically using AI systems to kind of come up with bird species. So in the end, birding is a unique domain where there are non-experts such as citizen scientists and experts such as ornithologists that interact with the same AI tools, such as one that helps you classify a picture of a bird. But so both types of humans might be impacted or impaired by those incorrect explanations. So basically in this interaction with the AI. And this is in the end why we chose this birding domain. So let's talk about the AI system and the explanation techniques that we used. So first of all, we looked into two different explanation modalities. First, we looked into text-based explanation, so natural language explanations, especially with all the recent developments and innovations around large language models. And we also looked into visual example-based explanations. So basically, kind of like normative examples in a visual way, where just where just visual images of the AI predicted class are shown. So more or less, if we look a little bit deeper into that, in order to generate those natural language explanations of bird species, we leveraged a model by Hendricks et al. And this model from Hendricks is based on attributes that are more or less within the image. So what we already saw earlier is, based on this model, we can generate explanations that more or less describe the bird in a visual way that is seen in the picture. For example, in this case, it would be, okay, this bird has a yellow breast and a gray head, for example. So for the example-based explanations that are way more visual, we decided to go with this normative approach. So basically, for this, we use all images that the model has seen during its training, and then the AI is coming up with examples that it has seen based on its prediction. So for example, in this case, the explanations are aligned with what the model has predicted. So here we see 3 magnolia warblers. However, sometimes, of course, this explanation can be also incorrect, and the model is actually not showing what the AI has predicted, but can also choose some other bird images that are super similar to the predicted class, but are just showing a different bird class in the end.
Awesome. Yeah, so based on those explanation modalities that we were looking at and our research questions, we designed a pretty rigorous, large mixed methods study for this bird identification task, which I'll briefly walk you all through. So first we gave participants a bird species identification test to determine their domain expertise in birding. They all saw the same 6 birds for this test, and we crafted the test to include 3 easy common birds and 3 harder common birds, by talking with expert birders to help us craft that. So the common birds were just like a hummingbird, a gull, a woodpecker, and the harder birds were more difficult species like a warbler or a vireo or I forget the other one, but birds that were more difficult that a regular birder would not know off the top of their head. So next we assigned participants to either see natural language or example-based explanation. So that was the between subjects part of the study. And just to reiterate, all the explanations that we used in our study were the real outputs from the model, and we didn't fabricate any of them. And in our user interface that participants had seen, this is how they saw the natural language explanations. So it was shown right below the image of the bird and prediction. For the example-based explanations, these were generated based on the extracted features of each image in the training set, and then we ran a cosine similarity, like a similarity algorithm amongst all the embedded features. And the example-based explanations were presented as 3 images with a short sentence framing what those images were, which kind of makes this like a mix of natural language and visual. So for the main bird identification task, participants saw 12 randomly selected birds in 2 different phases. So first they were simply provided a picture of the bird and they were asked what bird they thought it was and how confident they were. And then the second phase, they were shown the AI's prediction along with, they had the option to change the prediction and assign another confidence level. Each participant saw 4 explanations with those birds that had an assertive framing, 4 with a non-assertive framing, and 4 with a neutral framing. And for the natural language explanations, that looked something like this. So we used words like might be and appears to be for non-assertive, and definitely and clearly for assertive, and then no adjectives for the neutral. And for the example-based explanations, we use the same words for each framing to describe what those three images represented. Lastly, we selected birds and explanation pairs to show each participant such that they saw 3 cases for those 4 different scenarios, but in a random order. And not all participants saw the same 12 birds, so we made sure that it wasn't just based on the difficulty of trying to classify a given bird. So for the first scenario, the AI and XAI advice were correct, and for the example-based explanations, this is that type of scenario that we've gone through already, and the natural language explanation, we see that it's aligning with the predicted class here of a magnolia warbler. Just as a note, we were corroborating these natural language explanations with the predicted class by using Cornell Ornithology Lab's All About Birds ID information so that we could ensure whether the explanation was actually correct or not. When the AI advice is correct, but the explanation is incorrect, that means that the explanations do not align with the predicted class. So here, this example, all the images are of all of the different bird species, and none of them are Nashville warbler either. And the natural language description mentions a gray head, as we've seen earlier, which is not a characteristic of a male cerulean warbler. So in this case, the AI advice is incorrect, but the explanation is correct, which means that the explanation aligns with the AI advice, even though the AI advice is wrong, but it's still faithfully describing that predicted class. So this scenario, we can see that the example-based explanation shows 3 yellow-breasted chats, which align with that predicted class. And even though the natural language explanation says a downward pointing beak here in the image, we don't see that downward pointing beak, although that does align with Bewick Wren's. And lastly, the AI advice can be wrong and the explanation does not align with the predicted class. So for the example base, we've seen this example earlier, but we have the white-crowned sparrows and those do not align with the dark-eyed junco prediction. And for the natural language explanation, we have a description that does not align with a yellow-billed cuckoo. So after participants completed the identification task for 12 birds, they were shown a post-survey where we gathered extra information, such as which scenarios they would prefer to see assertive versus non-assertive framings in explanations, but we won't be diving into detail on that, so please refer to the paper for those analyses.
Yeah, cool. And so let's quickly talk about how we actually recruited our participants. So we used different platforms, for example, the AI for conversation, Slack channel, or different Slack channels. We also contacted several Audubon institutions within the US. And lastly, some participants were also recruited by Prolific, just by filtering for bird experts. Okay. So for those 136 participants, we kind of had to make sure that we correctly put them into the correct group. So basically to kind of investigate which are actually the experts and who are the non-experts. So for this, as Katelyn already mentioned, we had this bird species identification quiz, and by clustering then based on the participants' results, we see that we had overall 39% non-experts. So those were like 53 participants, and we had 83 experts. And for each of those groups, approximately half of them have seen the natural language explanations, and the other half have seen the example-based explanation. So for both groups, it was totally balanced in terms of the explanation modality. So we actually double checked that our results are also legit by looking into how did they actually score within the bird quiz. So let's quickly have a look in how their scores actually were represented by distinguishing between non-experts and experts. So we can see that for all the easy bird species that we displayed, participants or non-experts were actually able to correctly classify the family. So by this, we could make sure that at least those non-experts also had some knowledge in birding. However, when in terms of actually then classifying the correct species, they already had some issues. And if we then look at the hard examples, we can see that the family score was even lower and the species they almost didn't have a chance. Compared to the non-experts, however, our experts were especially good throughout the quiz. As you can see, for actually throughout all the easy scores and the hard scores, they achieved quite good performances. So kind of like underlining that our strategy in order to cluster non-experts and experts was done correctly. So in order to answer then our research questions, and just as a small recap, the first one was that we wanted to look into how imperfect explanations are impacting the decision-making of humans, and we also wanted to know how the level of expertise and the assertiveness of an explanation is impacting this relationship. This is the research model. And we conducted a moderation analysis according to Hayes. And the results of our moderation analysis were actually super interesting. So first of all, we can see that for both modalities, so for the natural language explanations and the visual example-based explanations, the level of expertise is moderating the effect of correctness of explanations on rare. So just quick recap, rare are all the cases where the AI is correct, the human is initially incorrect, and is then correctly relying on the AI advice. So in all those cases, the level of expertise, so basically how much a human knows, is moderating the effect that those incorrect explanations or imperfect explanations can have on their decision-making behavior. However, we didn't see that the level of expertise did moderate the relationship of imperfect XAI on RSR, and we also didn't see any moderating effect of assertiveness. However, what we could also see is that the correct explanation did have a direct effect on RSR. So as I was just mentioning, we didn't see this moderating effect of level of expertise, but we can see that actually the imperfectness of explanations is directly impacting how people rely on their initial decision in this AI-assisted decision making. So from that point of view, we could also already find first insight into the impact of this correctness of explanations on the human decision making. So then we further delved into how the human AI team performance is actually impacted by it.
Okay, so let's look at how complementary team performance is impacted by expertise. So complementary team performance, remember, is achieved only when the human and AI perform better than the human or AI alone. So in our study setup, to reach complementary team performance, the human AI team performance must be above 50%, since we chose to show everyone 6 cases where the AI prediction was correct and 6 where the prediction was incorrect. So looking at the experts first, the blue bar represents their performance before seeing the AI advice. And now the dark gray bar represents their team performance after they were shown the AI advice. And the light gray bar represents the AI performance, and performance is reported on the y-axis. So we see that the experts for both explanation modalities were performing better when collaborating with the AI and achieved complementary team performance here. But we didn't see that complementary team performance for the non-experts. However, we did see that their performance greatly increased when collaborating with the AI, which is good to see. So overall, as a summary, we saw that complementary team performance is impacted by decision makers' level of domain expertise. Specifically, the experts are benefited by having that AI system there to perform better, and non-experts didn't reach the complementary team performance, but they still improved. So we just saw how complementary team performance is different across different levels of expertise, but how does the correctness of explanations impact that team performance? So for experts, we see only a minuscule difference between their team performance when shown correct and incorrect explanations for both modalities. And this is probably because they are experts and they're able to rely on their expertise when the AI or XAI advice is incorrect. But looking at how incorrect explanations impact the non-experts, we see that there is a big difference between when they are shown a correct explanation and an incorrect explanation for both modalities here. And so the non-experts were deceived by incorrect XAI advice, which is hurting their team performance a lot. Oh, you're muted, Philip.
Sorry, classical issue. So basically with those insights, we can see that experts were actually not as much impacted by the incorrect explanations compared to the non-experts. However, they were still negatively affected. So this potentially impairment of the experts can still be due to, even though they have the knowledge, they can still be deceived by those incorrect explanations. So based on those findings, we further wanted to understand, okay, how does actually this incorrectness of explanations now deceive decision makers, and also distinguishing here between experts and non-experts. So for this, we basically come back to this conceptualization now, and you can see this conceptualization of appropriate reliance or AI-assisted decision-making is more or less framing our study here. So just as a short recap, relative self-reliance are all the cases where the initial human decision is correct and AI advice is incorrect. And we are now interested in how often the human correctly relies on their own decision out of all the cases where the AI advice is incorrect. And here doesn't matter whether the XAI is correct or incorrect. However, with our metric, we exactly want to understand this aspect. So basically, how does now this relative AI reliance changes for the decision maker when the XAI, so basically the explanation is correct or incorrect. So with this, you can hop on the next slide. So we can see that basically when we, so we can compute now the relative self-reliance for all the cases where the human initially is correct, the AI advice is incorrect, and now look into, okay, how does the incorrectness, so basically when the explanations are incorrect, deceive the decision maker by first computing the relative self-reliance for correct XAI advice and then for incorrect XAI advice. And we can do the same thing for relative self-reliance, relative AI reliance. So here we look on relative self-reliance. We call it deception of reliance for relative self-reliance. And we find in our study that experts are actually negatively deceived. And that just means that for example-based explanations, we see that this negative effect is deception of reliance can just be found by that the AI prediction is incorrect. However, the explanation is completely correct. So in this case, you can see that 3 times actually the the XAI system is showing, okay, it's a yellow-breasted chat. So basically, it's super convincing. Also, the bird that is shown is super similar to the ground truth image on the left side. And by this consistency, experts can even be conceived. But we only find this deception for the visual explanations, for the example-based explanations. We do not find this for natural language explanations, which is super interesting. At the same time, we can also then look into, okay, how is the deception now for relative AI reliance? So basically what I was just talking about. And here we can see that experts have a positive deception of AI reliance, and non-experts even have a higher one. So let's quickly recap that, what that means. So basically, the AI prediction is initially correct. The XAI, however, so the explanation is incorrect. So it is not aligning with what the AI is saying. And in this case, so we again looking at the example-based explanations because we only have the finding for the visual explanations. We see there's a strong inconsistency in the examples that are shown. And I mean, if I would be the decision maker and I see the AI is predicting the Nashville warbler and then giving me such an explanation, I would kind of assume, okay, the reasoning behind the AI system is completely incorrect. And of course, then I would also go with another decision. So here we can see how this incorrectness of explanations can deceive both expert and non-expert decision makers in those example-based cases.
So, what do we gain from all those findings there? Well, first, we gain this new conceptualization of human AI collaboration with Imperfect XAI, that we encourage future studies to explore new analyses in human AI collaboration with. And then what do we learn from using that new conceptualization? Well, just to recap in summary, in terms of the level of expertise, we learned that experts can achieve the complementary team performance despite the presence of imperfect XAI, regardless of the natural language or example-based explanation modality. And for non-experts, we see that even though they had imperfect XAI, their performance was still improved to be almost as good as the AI. We also learned that when non-experts are shown incorrect explanations, this negatively impacts their performance much more so than of the experts. And lastly, by measuring that deception of reliance, we observed that the example-based explanations are more deceptive than the natural language explanation modality. And specifically, experts were deceived by those correct explanations when the advice was incorrect. And the experts and non-experts were deceived by incorrect explanations when the AI advice was correct. So ultimately, we hope that all these insights can guide researchers and practitioners on how to assess and design for imperfect explanations in human AI collaboration moving forward. We'd like, oh, this is Philipp.
No worries. So overall, we'd like to thank you everyone for taking the time to listen to our talk. Also, a big shout out to all the in-person meetings at conferences, because this is actually how Kate and I met. So we both attended Kai last year, and then suddenly we ran into each other since we were both doing some studies with birds. So it seems like we're both the bird experts at our institute. Yeah, and overall, this in the end sparked up the collaboration, which was a super cool endeavor. So thank you.
And it's still ongoing.
True.
Yeah, thank you, everyone.